The example that I want to present to you, it's a relatively simple example of the foundation on sand. And it is worth highlighting that this is an example that was based on a prior example. I think it was developed by under leadership of Trevor Orr at the time. Although it was unpublished, those examples were also those, let's say, old examples. Were checked with first generation, and we redo that check with using the second generation Eurocode. So in this specific case, the basic assumptions are that the structure is assigned to consequence class CC2. So that's one thing that we have to use consequence classes in the second generation more often. There is a new concept in Eurocode EN 1990 called structural sensitivity class. We haven't spoken about that. It's basically not for us to deal with. It's for more structural designers. But in this case, it was SSC3, and this is related to the limits of deformations, and it's relevant for the check of the settlement later. So, in the example, we assume that the foundation is a simple square footing. We assume thickness of 1 meter and that it's embedded at the depth of 1 meter as well, and the load is applied at the top of the foundation, so it's basically at the ground level. So of course, to that we need to add the self-weight of the foundation. No ground inclination is considered in this example, and no removal of overburden next to the foundation is permitted, which means that we can consider that factor contribute to bearing capacity. So first we have to start with representative actions. Of course, we will have some superstructural load, so this will be permanent load together with the foundation self-weight. Then on top of that we might have variable load imposed from structure, and also in case of horizontal loading and moment loading, for this case we assume that there might be some wind. And what's important for considering the combination of actions is that those are two separate variable loads, so wind and imposed load from the structure. And the question is, what is the width of the foundation? What should be the size to accommodate those loads with the second generation Eurocode 7? So, concept we all heard about quite a lot already, but it's worth mentioning in terms of spread foundations, what that means in numerical aspects, so zone of influence. There is specific way of calculating it. Of course, those are approximate calculations. In Annex B, we can find how we can estimate that extent of the zone of influence. In this case, it was assumed that it's approximately 2 to 3 times of expected foundation size. Of course, to conduct ground investigation, which is not part of this example, we would need to have this kind of first approximation. So it's 4 meters, and that's considered as the vertical extent of the zone of influence. Horizontal one is not really relevant for those calculations presented here. So in this zone of influence, we learned that we have only medium dense silty sand from ground level to a significant depth. So we can assume that it's more or less homogeneous ground conditions. Then groundwater level, we assume that it's at the ground surface level. Selection of representative values of parameters was beyond the scope of this example, although in practice it's one of the major aspects of the design, and those are the presented values. However, one interesting thing we use here for the Young modulus, since in original example I believe the value was selected supposedly on basis of CPT testing, which not necessarily is that reliable for Young modulus estimation. So the idea is that we selected two values, lower and upper estimate, as inferior and superior representative values of considered stiffness, and the code allows us to do that. It's worth doing that, especially if the uncertainty is relatively high in prediction of one specific value. About factors, already Kerstin explained quite a bit about that, so I can just show you that we have to basically jump between those different parts. Interesting thing that might be worth mentioning in Eurocode EN 1990, this is actually the table, the upper one here. It's for buildings, and usually so far what was talked about in different presentations regarding actions, it was referencing the factors presented here. They are not that much different, but there are some differences regarding specific actions when we jump to other structures. So for example, for bridges, we have to look in different part of that annex in EN 1990, and at national level, some countries theoretically could come up with different values for different kind of structures. And of course, that additional check whether the horizontal load is not too big, it's related to the reliability of that check if we don't factor it, if we factor only the effects of actions. So it's worth highlighting that first, what we should start with is actually identifying possible design situations, and this is critical for the design. So in this case, three load combinations were considered. First one, when imposed loads, the variable loads are dominant in this case compared to what I showed you before, and then the wind load is factored with combination factor. So I don't show in detail those factors here. Those are the factors presented in EN 1990 when we have different kind of variable loads interacting, and we just don't take maximum values for all of them. Usually those combinations should come to us from structural designers. Then the second case we can consider are where wind loads are actually a dominant variable, so the horizontal action and moment acting on the foundation, and the third one where vertical load is acting favorable. So this is actually the case we have to consider, for example, for sliding purposes, or if we want to increase the eccentricity, considering that check for higher eccentricity value of the load. Next interesting development is design width of the foundation. So as usual, we have to calculate the effective area of the foundation, but for those purposes, we should consider, for ULS check at least, we should consider design width, where we have this additional delta B factor. So if we have measures specified to control the dimension of the foundation, it is basically zero. We don't have to consider that. But if we don't specify measures like that, they won't be implemented at the site, then we should decrease the design width. And the default value is basically 0.1 meter, so 100 millimeters. Also, it's important to consider that those should be the design values. Verification of the bearing capacity is basically the same as it was before. The basic concept, at least, as mentioned, overturning verification is included into that check. The resistance for single homogeneous ground layer under drained conditions, at least, is checked with the equation we all know quite well. In this case, out of those three parts, we don't have to consider contribution of effective cohesion, as we deal with sand with assume zero cohesion value. And it's worth repeating that the main equation is in the main part of the code. There are non-dimensional factors that are defined in the Annex B. This is how all of them, how they look like. I don't show all the numerical calculations from Excel spreadsheet where they are implemented. What is important are the numerical results that come out of those different combinations. And it's worth highlighting here again what also Kerstin already mentioned, that for material factor approach, so basically ABC, we either do A and B, which is similar to design approach 1 from the combination 1 and combination 2 from the first generation, or we do C, which basically combines those together and is quite more conservative than this dual check. And when comparing, or rather targeting the foundation size to get maximum utilization for those different kind of verification combinations, we can actually look what are the differences in the foundation sizes, and we can see that there are actually some differences occurring. Some of them are more conservative, some of them are less conservative. In reality, it will depend on our countries. Basically, at national level, we will have to specify which calculation, which verification case we prefer, which we recommend for specific kind of foundation. And I would recommend doing this kind of relatively simple exercise also at the national level to try selecting the best verification case you would prefer. What is also interesting, which I'm not sure if it was used before in many countries, at least it wasn't in Poland, when we consider other consequence classes, we have those extra consequence factors. Either applied to actions or effect of actions, or to ground properties, which basically modify the default values of the partial factors, and they are actually influencing the foundation size when implemented into the calculation. So, what if we were in consequence class 3, so higher class structure requiring a higher reliability level? The foundation size would have to be larger. It's simple like that. This specific example show that there is actually a difference, that in case of a material factoring approach, that foundation size have to be slightly larger than in case of resistance factoring approach, where the consequence factor would be applied to the actions. Just for clarity, in this case, the dimensions of the foundations for the purpose of targeting the maximum utilization, they were rounded up to 1 centimeter. In reality, of course, for construction purposes, we wouldn't specify. Yeah.
This question where to put this in fact KF or KM, is it optional? Can we put it wherever we want it? I on the note on the material.
No, like we put only on one of the things.
One, which one? Is that an option? Is that?
Like basically, if you factor material properties, it makes only sense to put it. I don't remember now how it's written exactly in the text, but basically it makes only sense to put it on the material factors. If you factor the actions, so for resistance factoring approach, basically the only option is to put it on actions, or rather the coefficients, safety partial factor for action, because it's modifying the safety partial factor of safety.
Does it mean when you use this M2 factor, you always have to put the KF factor on the
But basically, I mean, if you go to 1990 and find the table with the verification cases, you see that for VC1, VC2, and for VC4, there is a KF factor. And then basically, if you use those 3 verification cases, you already have considered the consequence classes. So it's only if you use VC3, the material factor approach that you often use there, that you actually can have the Km factor on VC.
And that's an automatic.
It's an automatic, yeah.
The one particular case is the verification case C that I think it's specified. I don't remember now the whole phrasing, but it's specified that we should put the partial factor on the actions.
Yeah.
Not we never combine or choose which one we want to do. Theoretically, there is an opening for putting it on resistance, but it's more theoretical because for spread foundation is not used, and as far as I know, none of the geotechnical structures actually allows for putting it there. I think it's something that comes from EN 1990, if I'm not mistaken. Okay, so sliding resistance. Not much has changed actually in that regard. We can consider the resistance at the base and at the face of the foundation. In this design example, the passive resistance on the side is ignored. Usually it has minor contribution, and personally I'm not in favor of using that because of what might happen in the future, and also compatibility of strains and how the mobilization of that capacity on the side of the foundation is compared to mobilization at the base. The equations are slightly different, but basic underlying concept is the same. So depending whether we have material factoring approach or resistance factoring approach, and here is also distinction between verification case 1 and 4, we have those three different equations. For the purpose of the design example, full friction was assumed between the cast-in-place foundation and the ground, so the interface factor is assumed as 1. And this is how the results of those calculations are actually, how they look like, and this is only for one load combination, which is the one with the favorable vertical action. This is something already mentioned by Kerstin, so we have to check as SLS this potential for physical gap forming under the foundation. And also in this case, for this example, the main check is actually the settlement check. So for that purpose, I've checked it only with consideration of vertical load, and it's based on the Annex B method presented in the code. What is important, this annex is informative. So if in your country you have some preferred method for calculating settlements, you want to use that instead of what is in the code, it depends on what will be decided at the national level. You might replace that method, you might allow for use of alternative approaches for the settlement calculations as well. What is in that informative annex is not really obligatory. And the serviceability limiting value in terms of settlements is considered to be 30 millimeters. That value is derived from Annex to EN 1990 for this SSC3 class. And usually those values should be used if there are no specific requirements for that project. So if we don't have any functional limitations, or the structural designer they don't provide us with any limit, we can use those values in that case. And settlements are calculated for one selected case using that simplified method for which you can see the equation here. And as I mentioned, it was calculated for the lower estimate and upper estimate of the Young modulus, giving us upper bound and lower bound estimate of the settlement. Here is the influence factor for that method also that was used, and the end result is the range of settlements. And personally, I'm in preference of instead of targeting one value, if we have high level of certainty, it's actually calculating a range of settlements that might occur. And as we can see, all of those, even the upper bound prediction, are within the specified limit based on what we have in EN 1990. Okay, so what are the conclusions? First of all, for this particular case, the required foundation width is found to be a bit different depending whether we use RFA or MFA. So this is something to be considered at national level, because one will be more conservative than the other. At least for this particular case, maybe for some other design cases, it might end up being a bit different. So different factoring strategies lead to different required foundation sizes, and we can define something we prefer in the national annex. Quite often it will be just to match our pre-existing design practice, as the general idea for calculation is not that much different. The values of partial factors are similar to the first generation Eurocode. So we might, if we don't have any better idea, we might target what we've done in the past. And it's worth repeating that there is some increase on foundation size if we consider the higher consequence class, and it's more noticeable in case of MFA approach. So I would recommend running some calibration exercises to prove that the reliability level is actually achieved. Thank you very much.